Hello and welcome to this EE228 video. This is a topic in chapter 2 of Navi's book, and it's the topic of beats and beat frequencies. And this phenomenon arises when we try to add cosines with differing frequencies. So let's start with x1 of t is a cosine with frequency omega 1, and likewise x2 of t is a cosine with frequency omega 2. If omega 1 over omega 2 is a rational number, then x of t will also be periodic. Right? We can either look at the greatest common divisor of omega 1 and omega 2, or we can look at the least common multiple of the periods. But otherwise, we can still do this procedure. In fact, even if they are a rational number, we can still do this procedure. So I just want to point out that this procedure works regardless of whether the sum of these two is periodic or not. So x of t, we'll define that to be the sum of the x1 signal and the x2 signal. And here I'm just going to use a trig identity that says if you add two cosines, you can write that as the product of cosines at different frequencies. So those two frequencies are half the sum and half the difference. Okay, and that derivation, that the adding two cosines to different frequencies, you can write it as the product of two cosines, that's probably worth a video in its own right. It's a cute little application of Euler's formula, but we can rename, because this is now a cosine with a certain frequency. I want to call this the carrier frequency, and I want to call this one the beat frequency. So I've got cosine double amplitude omega carrier times t times, not plus, but times omega beat times t. So here cosine omega c will be greater than omega b, right? Because we're adding two things divided by 2 rather than their difference divided by 2. And we see that as omega 1 approaches omega 2, the beat frequency goes to 0. And regardless of where they are on the spectrum scale, the carrier frequency will be larger than the beat frequency. So if I wanted to try and plot this x function, what I could do is I say, okay, I've got an amplitude of plus minus 2 now, and I've got a slow frequency cosine multiplying a high frequency cosine. So if I just kind of sketch this slow frequency cosine, and I'm also going to sketch its inverse to help me draw. If within that, I can think of this, along with the 2, acting like an amplitude on this cosine. So I have a cosine omega ct, I have a carrier cosine whose amplitude is changing with time, and whose amplitude looks like, apologies for my sketching technique here, but the idea is that we've got a high frequency carrier cosine whose amplitude is itself changing with function of time. So this inner cosine wiggles at frequency omega c, and this dashed cosine wiggles with frequency omega b. And so the application, or where you may have heard of this phenomenon before, is from your physics classes, or if you have a music background, this is a way to see if two instruments are in tune, and that would be playing them both at the same time and listening for these nulls, because this is what your ear is actually doing this summation. Your ear will sum the two pressure waves that are incident to it from the two different instruments, and when these nulls, these zero volume instances, get further and further apart, that means that the beat frequency is slower and slower and slower, which means that omega 2 is approaching omega 1. Okay, so that's a quick and dirty way of tuning two instruments just using your own human ear.